In this series of videos I've been looking at a ZAX ICD178 for a Z80 processor. So it's an in-circuit fault finder, debugger, emulator, and what I've been doing is initially going through and repairing it, but I didn't really show many of the repairs. This video series is more about developing some Windows software to control it, and its only interface is an RS-232 port. So it's fairly limited as to what you can see. It's really meant for use with something like a dumb terminal. There is some software you can get for it, which I do actually have. It's DOS software, but you don't get that much additional functionality, at least not in the area that I really want to use this. And hopefully as we go through the development of the Windows software, you'll see the thinking behind the software and why I'm developing it. And I've made some progress with the software, so we'll have a look at that in a few minutes. I want to try and explain in this video what the thinking is behind the software and what I ultimately will mostly be using this machine or this device for. Before we get to that, I just want to clarify some of the terminology I'm using and why. And whenever I make a video, I always try to be as precise as possible with the terminology that I use, just to make the videos as clear as possible. There's always some people who want to contradict what I'm saying, so I just need to clarify some terminology. In an earlier video I mentioned that when I was sending commands through to the ICD from the terminal emulator, I was compiling a program into the debugger, and someone commented and said, no, what I'm actually doing is assembling. Well, no, I was compiling. And I just want to explain the difference and why I use that terminology here. It is fairly important to make the distinction, otherwise as we go through this series it's going to get very confusing as to exactly what's going on and where. So just before we get on to the main purpose of this video, when you work within a pure software environment and you write software, you generally write one or more source files. It can be in C or assembly code or another language. It could be any number of languages. C is normally referred to as a high-level language, and assembly is normally referred to as a lower-level language. But it depends on what you're doing as to how you classify them. But it all generally works the same. The source files are taken and they're either compiled or assembled depending on what the particular source file is. The term you use is irrelevant. I'm not the speech police. It doesn't really matter as long as you understand the process. But the point is the source code is taken, put into what's normally referred to as an object file. And this process has to take into account the various language specific build requirements for the particular source code, but it puts it into a fairly standardized form. These object files are then all fed into a linker, and the linker's job is to allow jumps that are specified between addresses to make sense between the different modules. So if there's a jump in this source file, for example, where the destination is in this one, then that has to be taken care of by the linker. Otherwise, in the final executable file, the jumps wouldn't work. So the overall process, this entire process, is normally referred to as building or compiling. So although there's something here that's normally referred to as a compiler, you can also refer to the same level between assembly and the object file as a compiler as well, because this overall process is really compilation. That's specifically what it means. That's the actual meaning of the word. And also, if you don't have any C files, if it's all assembly, then of course the compilation is only for assembly files. So this is the process that we were going through in the video I was talking about. So I was actually compiling code, not assembling it. The assembler is actually in the ICD, so this is actually inside the ICD itself. What I was doing was this overall process, and so I refer to it as compiling, As I say, it doesn't matter what you call it as long as you understand the process, but the important thing to understand here is despite the fact that I'm developing Windows software, I'm not developing the assembler or the compiler. The assembler is inside the ICD, and the process, the overall process I'm carrying out is compilation to end up with an executable file that again is residing inside the ICD. So I hope that makes sense. So this is what I'm sending from the Windows software or the terminal. This is inside the ICD. This doesn't really exist. This is kind of, if you like, in my mind, as is the linker. So if I want to jump, I have to figure out where it's to. And then the overall process is taken care of, ultimately ending up with something that will run on the ICD. So I hope that makes sense. I also hope it makes sense as to why I'm using the terminology that I am. So on to the main purpose of this particular video, which is to try to explain what I want to achieve with the Windows software. Now, when I do reverse engineering of firmware for a particular machine, normally it means extracting the code from the ROMs, disassembling it into what amounts to pseudo source code, but then I have to go through and try and figure out exactly what's going on so I know what the machine is trying to do. I normally use the logic analyzer for that, and I showed a portion of that for this particular project. These are some of the notes I took when I was reverse engineering the ICD for the Z80, and there are reams and reams of this. It's a fairly long-winded and lengthy process, very tedious, but all I'm really doing is going through instruction by instruction, following it through on the logic analyzer, and then trying to figure out what all this does. And really I'd like a tool that would, if not automate, at least simplify a lot of this for me. So that's what I'm trying to achieve with the software I'm writing. So it's to replace a lot of the legwork that I'm currently doing with the logic analyzer. It's not going to replace the logic analyzer, but hopefully it will make the overall process a lot more straightforward. So we'll go across, we'll look at the software, I'll explain how far I've got with it so far, and hopefully you'll see the direction that I'm heading with it. Plugged into a ZX81. The ZX81 is powered up, and I have the clock input to the ICD set to the target. So in other words, it's using the ZX81 clock to capture data. So as you can see, the interface is fairly straightforward. I wanted to keep it as plain as possible. This isn't going to be the final version, this is just rough and ready. I've been dropping things onto the interface just to test out various ideas and try and get the software as functional as possible. So the first thing I wanted was the ability to see the CPU registers. So I've got a panel here that allows us to see that, and we can of course modify any of the registers. You can see that appears in the console, and when we update you can see that that change allowed us to change the value of the A register. So in the console itself, in the console area, is this black window. The red items is information we're sending to the ICD, and everything in green is what's coming from the ICD. That allows us to keep fairly good tabs on exactly what's going on with regards to the communications between the software and the ICD itself. And from that point on, I wanted to just get all the commands that are available in the ICD implemented in the software in a way that makes them as clear and easy to access as possible. So the next one I added was the breakpoints. So we can add breakpoints in exactly the same way as we would if we were using a terminal. So we'll add one here. Breakpoint in memory needs an address, instructions, and single pass, and we can add that. And notice that it sends this straight through to the ICD, and if we update this you can see that the ICD now has the breakpoint set. And I've taken a similar approach. Some are commands only, so for example trace, we can see what the current trace mode is. or we can set the trace mode to something different. So in this case, what I set it to all. Check that it's now set, and you can see we've now changed the trace mode. So it's quite quick and easy to do. Haven't really gained that much so far looking at this between what we had with the terminal and our new software, but from here on it starts to get a bit more powerful. So firstly, we can send code or information through to the ICD from within our program, and one of the things that I was really looking to do here was to make all this as streamlined as possible, but also retain information. So I created a structure of folders underneath the build folder for the software, and each of those folders contains different types of file, and currently this software generates about 7 different types of file depending on where they originate. So we'll look at them in turn as we go through the software. Now the first one is the one we've seen before, which is the hex file, and we can now send this directly through to the ICD. So if we select send hex file, and we pick the file we want, and it's taken us through to the appropriate folder. There's only one file in there at the moment, I'm just testing this, and we can click that and it now sends the file through to the ICD. We've got in circuit mode 0 set, so it's using all the resources within the ICD itself. And another window I've implemented is the memory dump, so we'll look at the memory range from 4000 through to 4100 hex. And you can see we now have some information there. So something else I've implemented is the fill command, so we can fill an area of memory with whatever character we want. So we'll use that and we'll set all these values to 0. So we can send it either as a hex value or an ASCII character. So in this case we're going to use a hex value of 00, and the starting address will be 4000, and the end address 4100, fill memory, and if we now re-extract the data from the memory, you can see it's now all set to 0. And if we send the file back down, and we re-extract the data, you can see we actually have our program, and we should now be able to run that program in the same way we did in the previous video. And as you can see, it's running. It should stop at the breakpoint, which it has, and now we can click on the button over here that's labeled history D, so that's history data, and you can see we can extract that. So this is not the source code as such, it is disassembled, but this is just line by line as each line is encountered. And we can do something similar with machine cycles and look at it in terms of the machine cycles that have been captured. We can also save this information, so if we want to use it at a future date, we just right click, save to file, and then we can save that information, or we can load from file. It will just load back in exactly what we save. But what I wanted was to be able to kind of semi-automate the process of going through all this and being able to extract the actual source code, because this is not, of course, the source code. This is just the line by line code as each line is encountered, and this is looping around, so some of these lines will be repeated quite a few times. So I've implemented something that was not available in the original system, and that is this trace buffer extraction. So what we can do now is click on the send button. It will do several things. It will go through this data and it will process it, and it will extract the source code that is included just in what we've captured here, but it will also send the instructions through to be compiled or assembled by the ICD. So if we do that, you can see it's finding each line and it's adding it. It won't duplicate lines, and it also sorts them to put them into the correct order as far as their address is concerned. It will keep going through till it's processed all the data, which it has done now, and so it's now effectively reconstructed the source code that was used to create this capture. And if we want to, again, we can save this to a file. So this effectively allows us to capture the source code from execution capture, which is a very powerful tool to have. And we can also do that from the machine cycles. If we want to, we can include the machine cycles in this. If we check this box and do the same thing again, just wait till it finishes, you can see it's reconstructing, but this time it's including the machine cycles. So that's complete. Do it one more time. In fact, what we'll do is we'll look at the memory dump and we'll clear this. So that's now clear, back to 0 again. And don't forget, this is the memory within the ICD itself. And if we now repeat this, as I said, it's not just extracting the source code, it's sending this back through to the ICD. Okay, so that's finished, but it's also now reconstructed the code within the ICD memory. So if we look back at the memory dump, notice the file or the program is now back there, and in fact we can run it and it runs just fine. We're in ICD mode 0 at the moment, so it's using all the memory and resources in the ICD itself. But if we change to mode 2, then it will use all the resource within the target machine, including the RAM. So if we pull back up the memory dump, same range of addresses, but notice this has now just got random code, and this is the data, the random data that was in the RAM of the ZX81 when it was booted up. And again, we can clear this if we want to now. Dump it again. Notice now it's full of zeros. So this is the RAM within the ZX81. And again, we can send it either the file using a send hex file, or we can send the data from the history. So we can now send this through directly from this window, the disassembly window. It will pull out the underlying code and it will send that through to the ZX81 RAM. And when it's finished, we can pull up the memory dump window again. And notice now our code is there. So if we now try and run this from the same address, it's running, but this time it's running from within the ZX81. So this is now running on the ZX81. So now we've got the same disassembly back, despite it having been extracted from running the program on the ICD, being processed, sent through to the ZX81, and now it's running fine. So again, very powerful tool to have. So the other thing we can do is if we look at the memory dump from address 0, we're in mode 2 still, so we're looking at the memory in the ZX81. You probably recognize this as being the ROM code in the ZX81. And what we can do is if we look at the, go to mode 0 and look at the same memory area, and this has got random data in, so we'll again fill that with zeros. We've now got zeros in there, and what we can do is copy data from one location to another. So if we go to command copy memory, we can copy in either direction. So we can copy from the target, in this case that's the ZX81, to the ICD, or we can copy from the ICD to the target. We're going to copy from the ZX81, and we're going to copy the address from 0 up to 1000 hex, and we're going to copy that to the ICD starting at address 0. So we'll copy memory. That's now finished, and if we refresh this memory dump, we're in mode 0, so we're looking at the RAM within the ICD. Notice we've now got the ROM code from the ZX81, but because this is the ICD memory, this is actually RAM. So if we want to, we can modify this. And then if we set up a memory map, we can run this code using the ZX81 hardware, but using the RAM version that's in the ICD. And because it's RAM, of course, we can modify it if we want to. So this is now approximating a modern ICD or IDE that we'd use for a modern microcontroller. It's quite a powerful tool to have, and it means we can go through, modify the code, run it, try it again, trace through it, run it, modify it, and keep going round, and it will help us develop new code or fault find. So the next question is how to set up the memory maps. So the memory map only makes sense in mode 1, where it's sharing the memory in the ICD and the memory on the target. See here, it's got a basic memory map. It's saying that everything from 0 to FFFF is P, which means it's all in the ICD. In fact, if we go through and dump the RAM area from 0 to 100, you can see it's got the source code for the ROM, but only because we copied it. If we now come to Command and Fill, I'm going to fill with zeros, which it has done. If we now dump this again, notice it's all zeros. However, if we switch to the mode 2 and we try and do the same thing, notice we're getting a write failure warning. And the reason it's doing that, if we try and dump this, then we haven't changed anything, because this of course is ROM, so we can't change it. But what we can do is go to mode 1, and then we can map different areas of memory between the ICD and the target. So you can do this in a long-winded way by typing it in, but I have of course included a memory map window. You can just type in the commands for memory mapping as you would in the terminal. But of course I've allowed us to save and load files from files on the PC. So in this case we'll load a simple memory map, we'll send it through to the ICD, and I've included, as you can see, a graphic to give us a clear indication of the current memory map. And if we want to change it, for example, down here we've got the first 4K, as red is the target and green is the ICD. So we've got two areas here where we've mapped the target memory into the ICD. We can change this if we want to go from 4K to 8. We just change the map, send it back down, and now notice it's gone to 8K. We can have more complex memory maps if we want to. So this one is a much more complex one. So green is the ICD memory, red is the target memory, and yellow is ICD or target that is read-only, in other words ROM, so it can't write to it. And if you try, and if any code tries to write into that area now, it will generate an error, so we can keep track of what the code is doing. So a very quick and easy and convenient way to configure and save memory maps. So that comes, there's a few other things in here as well that I won't bore you with just now. We will look into these in more detail in a later video. So we can search the RAM if we want to, looking for particular characters or values, and all the commands that are available on the ICD we can now get to from here. But one thing I wanted, which again you can't do from the ICD or the terminal normally, is to allow this all to be reconfigured fairly quickly. So if we update the breakpoints, you'll see we've got breakpoints set. If we look at the trace setting, notice we've got a trace mode set. But if I press the reset button on the ICD, notice we've reset. This is another reason I wanted this string to show up, by the way, which is why I modified the ROMs in the ICD so I could see it more clearly, and the software could detect a proper reset, which is what it's doing. But notice now we've reset the ICD, we've lost all these settings. You might have to do this on a fairly regular basis when you're fault finding and debugging. And although it's now much quicker and easier to re-add these, I wanted a more convenient way, and so I've included a scripting engine within the software. And this just allows us to write instructions and save them to a file in the same way we would if we were writing them into a terminal. So if we load one that I've already done, simple script, you can see it's very straightforward and simple, exactly the same commands as you type them in to the terminal, but we can run this and you'll see that it configures the ICD. If we now click on update, you'll see the breakpoint set, and if we go to commands and check the trace mode, the correct trace mode is set. And this script can be as lengthy as you want, so if you want to, you can have much more complex scripts that do many more things, or as many things as you want really. Anything you can do from a terminal you can now do through the script. It's a very quick and convenient way to set up a test procedure or process and to configure the ICD. So we can send files, we can extract the code from captured data, and the entire thinking behind the software is to greatly simplify and visualize what the ICD is currently doing, although it really doesn't do much more in terms of commands that you can do through a terminal. Extracting the code from the trace data is a very powerful addition, and being able to view things like the memory map and conveniently keep all these windows on the screen. All these can be open at the same time, so we don't need to keep closing them down. I'm closing them down because I'm recording this onto a video, so you can only see a small proportion of my screen, but normally you could leave all these open at the same time, spread them out and see exactly what's going on without having to keep switching between them. They all do update in real time as you use the software, so it's quite a powerful tool. It's coming along quite nicely. If you've got any ideas for additions or things you think I could add, then by all means please leave a comment, but hopefully you're now starting to see the potential power of this software. So the last thing we'll look at in this video is the ability to send assembly instructions to the ICD. And again, you can do this using the terminal, but what I've effectively done is something similar to the scripting engine, but within the disassembly window. So what you can do is enter what amounts to source code into the disassembly window, and the disassembly window, the software keeps track by virtue of the nature of the data in this window as to what the data actually is. You don't have to tell it whether it's history data of one form or another, or whether the history is machine cycles, or whether you put an assembly file in there. It will figure that out itself. So what we can do is just enter commands, and again I've written this in such a way that it's not particularly fussy about exactly how you lay this out. But so the first thing we have to do is give it the origin for the code. That's just the starting address, and then we can just start entering instructions. So these would be in the general format, the same format we would use if we were using the terminal. So if we want to put a value into the A register, for example, we can do it like that. If we want to load the B register, so I'm just making up random values at the moment, but the formatting is not important. I can put it in pretty much whatever form I want, as long as there's no rogue characters in there that it can't figure out. And like I say, we can keep going until we've got everything in there that we want. We'll clear the console window so we can see what's going on, and we'll now click on the send button, and what it will do is it will figure out that this is actually source code rather than history code, and it will send the instructions in the proper format through to the ICD. So before we do this, we'll just pull up the memory and we'll dump the values here, all been set to 0. And what I can now do is click on send. It's gone through. We'll pull back up the memory dump, and hopefully you can see it has sent the values and they've been assembled into the ICD memory. And of course we can load these from files. So if there's one, so as you can see, we can load this from memory and we can send this through to the ICD. This can be as long as you want, so you can just create your own source code. Now it does not, the software, as I mentioned earlier, does not contain an assembler or a compiler, so any jumps you'd have to work out yourself. I may well build a proper assembler into this tool so that it can work out the jumps, etc. But I'll have to think about that. It really depends on exactly how I end up using this. At the moment it's really meant as a fault finding tool, but we'll see how it goes. It might be worth building in a more capable assembler. Okay, that's it for this video. Hopefully you can see that this is coming along and it looks like it might make the ICD far more useful than it was before.